Okay, so today will be the last session where we will cover something mathematical and theoretical. Depending on how fast we go, this might also be our last session on cryptography, and then from the next session, hopefully we will talk only about cryptocurrencies. So let me share my screen. So in the last session, we talked about symmetric encryption. This was the very last thing that we covered. And the idea there was that if you want to communicate over an insecure channel, such as the internet, you can do that securely as long as the two sides have some shared secret key K. So as long as you have some K that only Alice and Bob know about, they can communicate. And this was the kind of definition and requirements that we had. We said that we should have an encryption function that uses the key K to encrypt a message. So it gets a message and gives you an encrypted version. And then there should be a decryption function that uses the same key K and decrypts the encrypted message back to the original message. And this was the requirement that we had. So if we encrypt a message and then we decrypt it with the same key, we should get the same message. And of course, in order for this to be secure, we had this other requirement that if you have some adversary Eve who can see all the communications and knows all the algorithms, but just does not know the key, then it should be impossible for this adversary to find the message. And actually this computing the message exactly is kind of a relaxed requirement here. The stronger requirement that we had was that we want Eve to find nothing about the original message. So we want her to not be able to find out anything at all. So one thing that I should tell you about cryptographic primitives before we go on is that I generally show you how we can create these functions, how we can create the encryption and decryption functions. But in our use case, when later on we want to use them to design a blockchain, all you need to know are the definitions. So we just assumed, for example, when we want to use symmetric encryption, that there is an encryption function and a decryption function that have these properties. We would never come back and talk about how we actually created these. So even if the mathematics gets too much for you, you can just remember what they mean intuitively. Like the intuitive notion of doing encryption and decryption is quite easy. And that would be pretty much enough for understanding what we will do in creating our blockchain. Okay, so the main problem that we have here is that we are assuming this key K is already shared between Alice and Bob. So for example, we are assuming that they have met in the real world and physically had a key exchange. So maybe Alice created the key and physically sent it to Bob. And then now they're using that key to communicate over the internet. Of course, this is not so great. So ideally, we like to be able to create this key without having it in the first place. So the question is, what happens if I want to communicate over the internet with someone? For example, I want to check my email, and we don't currently have a shared key. We have never met physically. I've never met my email provider physically, right? So how do I do this? How do I share this key? This is the problem that we want to solve today. So if I want to write my scenario here, it's that, again, I have two parties. I have Alice on one side, and I have Bob on the other side. And they are again connected by an unsecure channel. So this is the channel that they have. Let's again call it the internet. And this is not private, so any communication here can be read by others. And the problem is that they don't have a shared key K, and they want to create a shared key. So, how do I do this? How do I share this key? This is the problem that we want to solve today. So if I want to write my scenario here, it's that, again, I have two parties. I have Alice on one side, and I have Bob on the other side. And they are again connected by an unsecure channel. So this is the channel that they have. And this is not private, so any communication here can be read by others. And the problem is that they don't have a shared key K, and they want to create a shared key. our goal is to create a key K such that both Alice and Bob know K, but no one else knows it. Or let's say no adversary can obtain K. So at the first glance, this seems kind of impossible, because if you think about it intuitively, it seems like, well, we are doing this communication over the internet and we have an adversary, let's call the adversary Eve, who can pretty much listen on everything that we send. So if we don't already have a shared key, how is it that we can have some key K at the end of it, such that both Alice and Bob know the key, but Eve cannot compute the key? It seems impossible, but it's actually doable. And the process that I'm going to explain for this is called the Diffie-Hellman Key Exchange. Actually, Diffie and Hellman insist that it should be called the Diffie-Hellman-Merkle Key Exchange. So we can call it Diffie-Hellman-Merkle. Okay, so how do we solve this? Basically, the problem is that we want to have a shared value between two people, and these two people can only communicate over this channel, over the internet, but we want anyone else who sees all the communications to be unable to obtain the same shared key K, right? Okay, so here's the idea. I'm just going to first say what the solution is, and then I'll tell you why it is secure. So in the first step, so let me call it step 1. What Alice and Bob do is that they first choose a really large prime number. And we can say that, for example, Alice chooses that. So let's say that Alice, or maybe Bob, I don't care who does this, choose a large prime number P. And when I say large, I mean really, really large. So imagine that this prime number is at least thousands of digits long. Okay? And they communicate this P over the network. So let's actually do something here. I will show everything that is communicated over the network in blue and everything that is secret in red. So blue means it's public, everyone can see it. And red means it's private and it's not communicated over the network. Okay? So in the first step, they just choose a large prime, and this prime is actually going to be public. So what we do here is that, let me just erase this. Erase these as well. So let's say that Alice sends over this prime number P to Bob. And of course, because we sent it over the internet, over this non-private channel, we can assume that the adversary also knows about P. Okay? So our second step is that both Alice and Bob choose some secret number for themselves. So Alice chooses a secret. Let's call this secret A. And so the role of the prime number that we chose in the previous step is that instead of doing our calculations with general integers, we want to do our calculation with integers modulo P. So I always just take the remainder of division by p when I want to calculate with my numbers. So here, when I say that Alice chooses a secret, the secret that Alice chooses, A, is actually just a number between 0 to p minus 1. Okay? And this is a secret, so Alice is not going to announce this. So Alice will have A here. And Bob also chooses a similar secret B. So let's say Bob chooses a secret, and because this is a secret, I'm writing it with red, and this is also from the set 0 to p minus 1. Now, I want to tell you the intuition before saying what's going to happen next. So we don't want to publish A and B on the network because everyone else will see what we've published there. But we want to somehow be able to compute a specific number that only can be computed if you know A and B. And the number that we want to compute is actually of this form. So I want to fix some number G, and then I want to compute G to the power of A times B. And of course, all of this is modulo P. Okay. Now, what's the point here? The point here is that if I want to compute G to the power of A times B, I need to know G, and I also need to know A and B. So if I can somehow divide this computation between Alice and Bob, so that some of these parts, especially A and B, are not made public on the network, but at the end of it, both sides have the same number, G to the power of AB, then I can be pretty sure that this can be used as my key K. Okay, so this is the intuition, but let me just say how we do this. So in the first step, when we choose a large prime number P, we also choose some number G, and this G is also going to be in the set 0 to p minus 1. Okay, but additionally, I want this G to have another property. And the other property that I want is that if I look at the set of all powers of G, so if I look at the set G to the power of 0, G to the power of 1, G to the power of 2, and so on, until G to the power of p minus 1, I want them to have all the possible remainders when divided by p. So I want this set to be the same set as 0, 1 to p minus 1. Okay. For those of you who are a bit more mathematical, this means that G should be a primitive root modulo P. So I choose a G such that if I just compute all of the powers of G, all the first P powers of G, and I take their remainder when divided by P, I get all the possible remainders. Okay. So, and again, this G is also public. So we can again just assume that Alice chooses it, or maybe Bob chooses it. I don't care which side. But P and G are both public. Okay, now what is our goal? Again, what we want is that we want Bob to know G to the power of AB. And generally, I just don't write modulo P, but every calculation is modulo P here. So just assume that. So I want Bob to have G to the power of AB, and I want Alice to also know G to the power of AB. But I want these to be secrets. Okay, so this is AB. Okay, so I don't want the communication to actually reveal what this G to the power of AB is. Okay, so how can I do this? Actually, it's not so hard. This is the third step. I say that Alice computes G to the power of A and sends it over to Bob. On the other hand, Bob does the exact same thing, but with B. So Bob computes G to the power of B and sends it to Alice. So let's see what's happening here. So this is the situation that we have. Alice knows A, Bob knows B, everyone knows P and G. So Alice can compute G to the power of A modulo P because Alice knows all three of these things. So Alice can compute G to the power of A and send it to Bob. But now everyone else on the network also knows G to the power of A. Bob can also similarly compute G to the power of B because he knows G was public, he knows B, and all calculations are modulo P, so he knows P as well. He can just compute G to the power of P and send it over to Alice. Okay. But now here's the nice part. This is step 4. Okay. So we know that Alice knows the secret A, and Bob has now published G to the power of B. So what Alice can do is that Alice computes G to the power of B again to the power of A. Okay, and actually let me use a different color for this. This is G to the power of B. Okay. So why can she compute this? Well, because G to the power of B was given to her by Bob. This was sent over the channel. And she knows the secret A. So she can just take this number and raise it to the power of A. And of course, this leads to G to the power of AB. Similarly, Bob can do the same thing. So we just swap A and B. So Bob knows G to the power of A because Alice told it to him. And he also knows B because it was his own secret. So he can just raise this to the power of B. And Bob will also get G to the power of AB. And again, all the calculations are modulo P. Okay? So in this way, what we see here is that Alice now knows G to the AB, and Bob also knows G to the AB. But no one who saw the communication can figure that out, because if they just know G to the A and they don't know B, they can't compute G to the AB. And also if they just know G to the B and they don't know A, they can't raise it to the power of A and compute G to the AB. So what happened here is that now Alice and Bob have some shared value, G to the power of AB, which they can use as their K, the key that they had, for example, in the previous protocol for doing symmetric encryption. So now they have a shared value, and using this shared value, they can do the previous protocol or do any other cryptographic protocols that need a shared common value. Okay. So is this clear to everyone? If you have any questions about how this works, please ask now, and I will just answer them in the chat. Okay. So one question is, why does P have to be a big prime number? Well, so let's see what someone who's trying to attack this protocol might do. So suppose that I have some person Eve here who is seeing everything that is happening on the channel. And let's say that Eve now wants to figure out what K is, right? So Eve is seeing G to the power of A. So the question that we should answer is, if we know G to the power of A, can we compute A itself? And if P is a small number, then the answer is yes. So if, for example, P is just 1,000 or something small like that, and I know P and I know G, I can just easily brute force all the possibilities for A, right? So that's the reason why P should be a large number. But the question actually asks, why should it be a large prime number? Well, the other part of this is that we want to actually be able to find a G with these properties. We want to find a G such that the powers of G give us all the possible remainders. And this is quite easy when you work with prime numbers. So that's just convenience. If you have a large prime number P, you can easily find this kind of G, and there are many primitive roots there. Actually, any G that is relatively prime to P minus 1 is going to work here. Again, I don't want to teach you number theory. I just want to teach you cryptography and cryptocurrencies. But the reason why we're choosing a prime P is because it's easier to find these numbers G such that they have the property that we wanted. Okay. So the next question is, why should we require that the powers of G give us all the possibilities? Well, again, there are several points here. So one point here is that we want to really hide the data, right? So if the powers of G give us only a few different possibilities, then it would be easy to brute force again. But on the other hand, what we're going to do is this. So I'm sending G to the A. So Alice is sending G to the power of A over to Bob. And Eve is seeing that, right? So generally, we want to have a very strong guarantee. We want to say that not only Eve cannot compute A, but Eve cannot know anything about A by just seeing G to the power of A. And if G has this property, then when Eve sees G to the power of A, she can't know anything about A. A can be anything between 0 to P minus 1, right? Because G's powers can be anything. So again, this is just to give us a bit more security. Okay. So the next question is, why can't Eve do log to get A or B? Okay. So we'll answer that in a little bit. So another question is, how can G to the I be 0 modulo P? Oh, okay, sorry. Yeah, my bad, not 0, just 1 to P minus 1, and this should be until P minus 2. Okay, really sorry about that. Okay. So another question is that if we see G to the power of A and G to the power of B, can we compute G to the power of AB? Well, this is actually the security analysis that I'm going to do right now. So let me do this, and it's great that you guys got to this point already. So how secure is this key exchange? How secure is Diffie-Hellman and Numerical Key Exchange? So what are we assuming here? We are assuming that an adversary who knows P, G, G to the power of A, and G to the power of B cannot compute G to the power of AB. Okay, so let's write our assumptions down very clearly. So our assumption, so our security assumption, let's say, is this, is given P, G, G to the power of A modulo P, and G to the power of P modulo P, it is hard to compute G to the power of AB modulo P. Right? This is our security assumption. Because if an adversary can do this, then they can pretty much find our key. Right? And actually, the answer here is that it's hard because no one knows how to do it. So right now, we don't have any algorithms that can do this, especially when P is a large prime number. So again, imagine that P has thousands or maybe even tens of thousands, hundreds of thousands of digits. So P is a really large prime number. So in order to do this, you have to have an algorithm that is polynomial time, let's say, in the number of digits of P. So if you just have an algorithm that is polynomial time in terms of P itself, that's not going to be good enough. It will take forever to compute these things. So I can give you a very simple algorithm that is not good enough. And it's just trying to reverse these things, right? So suppose that I know G and I want, suppose that I know G to the power of A and I just want to find A. So I can just try by computing every power of G and seeing which power equals A, right? But this will take order P time. And P is a huge number. So I don't have enough time in the universe to do this kind of thing. Actually, there are much better algorithms for doing this, but still we don't have an algorithm that is fast enough. So right now, as of the time of this lecture, this is secure because we don't have an algorithm that, given these numbers, can compute this one. And actually, one specific case of this, which is a very famous hard problem, is what we call the discrete logarithm problem. So the discrete logarithm problem is this. It says given P, G, and G to the power of A, of course, modulo P, compute A. Basically, the problem asks you to compute a logarithm, but the difference is that it's discrete, and we are doing all of our calculations modulo P. And again, this is a very well-known hard problem. Like, people have been working on this for many, many years, and there are no good algorithms for it. So there are no algorithms that are polynomial in the number of digits of P and G. You can, of course, have an algorithm that is linear time in P, but that's not good enough because P is large. So it's widely believed that discrete logarithm is a hard problem. And it's also widely believed that this problem is a hard problem. So I can't give you a mathematical proof that this is impossible because that doesn't exist. But what I can tell you is that a lot of smart people have tried for a long time and they couldn't do this. So the security of this key exchange is kind of conditional. The idea is that if someone can break our key exchange, then they have solved this really hard problem, or probably even this one, which everyone agrees is super hard. So the way you should think about this is very similar to how we prove, for example, NP hardness to show that a problem is impossible to solve with polynomial algorithms. We don't actually know that NP and P are different sets of problems. It might be that you have a polynomial time algorithm for an NP complete problem. But what we know for sure is that we have tried for so many years and we couldn't find one. So nowadays, if you prove that a problem is NP-hard, people are convinced that, okay, it's probably impossible to find a polynomial time algorithm for it. Similarly, we have these kinds of assumptions in cryptography. For example, if you have some protocol and you say that this protocol will only be broken if someone can solve the discrete logarithm problem, then everyone is pretty much convinced that, okay, this protocol will not be broken. So again, this is not ideal, but this is the best we can do. Okay, so there is a question about the name of Merkle. Is there an association between Diffie-Hellman and Merkle in the context of Merkle trees? No, these are just all very famous cryptographers. And so Merkle invented Merkle trees, and he also had a very instrumental role in key exchange and public key cryptography. So his name appears several times. Okay, so another question is that, do we have any constraints when we set the value of G? Well, so there are some known attacks that can break this for some specific values of G or some specific values of A and B. So again, as in all cryptography primitives, what I would tell you is that you should not implement this on your own. You should just use a library that knows about all these attacks and chooses A, B, and G randomly so that they are not easy to break. Because again, this thing is hard in general, but it might be easy for specific values of G or for specific values of P, let's say. So for example, one case is like if P is very close to a power of 2, there are some algorithms that break this. Or if P minus 1 is can be written as a multiple of small primes, then there are some algorithms that will break this. So again, it's hard to break this crypto system in general, but for some specific values of G, A, B, and P, it might get broken. So again, you should just use a standard implementation that avoids those corner cases. Okay, so another question is that the number of primes is relatively small. Yeah, it tends to log n as n tends to infinity. So there are many more messages communicated, so many messages use the same P. That's correct, but also you don't need to use a prime number, a different prime number every time here. And also, even if you want to use a different prime number, it's not a big deal because you only use it to create your key. And after you created your key, you can just use the previous method and XOR in order to send as many messages as you like, right? And so, well, here actually we use the key K only once, but then you can then have some extra assumptions here. So for example, you can say that I use K for sending over my first message, then I hash it once and use hash of K as my new key for sending the second message. And then I hash that again and use the new hash for sending another message and so on. Or you can have any other kind of random number generator that uses K as its seed and gives you random numbers that are your next keys. So as long as you have the first shared key, it's not so hard to generate more keys that are shared. And you don't have to just repeat this process over and over again. Okay. So there is another question that if G belongs to the set 1 to P minus 1, do the powers of G give us all the remainders automatically? No, that's not the case. So for example, if you have 1, that's not going to work. Yes, someone else also said that. But again, the G's that have this property are called primitive roots, and you can actually just read about them on Wikipedia. And for prime numbers, it's really easy to find primitive roots. So it's easy to find a G that has this property. Okay. So I'm now going to move on to another scenario where we want to do public key or asymmetric cryptography for the first time. So here's the scenario that we have. Let's say that, again, as usual, we have Alice and we have Bob. And they are connected by a channel that is not secure. So I have, for example, the internet here. And let's say Alice wants to send an email to Bob. But the problem that we have here is that we don't want to have this kind of key exchange, because this kind of key exchange assumes that both parties, both Alice and Bob, take part in the protocol actively. So if you look at it, Alice first has to send something to Bob, then Bob sends something to Alice, then Alice sends something to Bob. It's interactive, right? So what happens if, for example, when Alice wants to send a message to Bob, Bob is offline. Let's say I want to send an email to you. I don't want to have to do an interaction with you and generate a key, right? I just want to be able to send my email to you. So this is the scenario that we have here. And so it's the same scenario as before, with the extra caveat that Bob is offline when Alice sends the message. So Bob is not always offline, of course. So if you think about how you work with your email, for example, you were online at some point when you created your email account, and then people can send you emails and you don't see them, but you will become online at some other point, and then you should be able to read the emails. So the assumption of Bob being offline only applies to the period where Alice is sending the message. So the idea is that Alice cannot ask Bob to cooperate when Alice is sending the message. Okay? So in this case, what we want to do is that we want Alice to be able to encrypt the message and send this message to Bob. And of course, this message goes over the internet. So we want to make sure that no one else, no one other than Bob can decrypt the message. And the way that we do this is what's called public key cryptography or asymmetric cryptography. And the idea is that Bob now creates two different keys. So Bob creates a secret key. Let's call that secret key D. And he also creates a public key, and that's E. So Bob just announces E to everyone. Not necessarily to Alice, but it's just announced on the internet. This is my public key. This is E. Okay? And the idea is that whoever wants to send a message to Bob should be able to just use this E to encrypt their message and send it to Bob. But then to decrypt these messages, Bob has to use D. And because only Bob knows D, only Bob should be able to decrypt the messages. So let me actually formalize the requirements that we have here. So the requirements are this. So we want to have, just as before, an encryption function. Again, we call it encryption, that gets a key and encrypts a message. So gets a message, gives us the encrypted version. We also want to have a decryption function. We call this decryption, and it gets also a key. and decrypts the message, right? So previously, when we were doing symmetric cryptography, we used the same key in encryption and decryption. But now we don't want to use the same key. We want to have two different keys, one for encryption, one for decryption. And we will announce the encryption key to everyone so that everyone on the network can send a message to Bob. They can just encrypt using E and send it to Bob. But the decryption key will be only in Bob's hands, so only Bob should be able to decrypt. Okay? So we say a key pair is basically just a pair where you have an encryption key, which is public, and a decryption key, which is private. So only Bob knows that, such that, okay, what are the requirements that we want? Well, the first thing that we want is that if we have some message and someone encrypts this message using E, so anyone can do that since E is public, so encrypts it using E and then sends it to Bob, then Bob should be able to decrypt this message using D. So the only difference with the previous case is that the keys for encryption and decryption are now different, okay? So that's the first property that we want to have. So if you know the decryption key, you should be able to decrypt the message. And the other property that we want to have is that if an adversary knows everything except the decryption key, they shouldn't be able to do decryption. So if an adversary knows, let's say, the encryption key, which is something that everyone knows, and the encryption algorithm itself, and the decryption algorithm, and also the encrypted message, they should not be able to compute the message itself or find out anything about it. They should not find any information about the actual message that was sent. And let me actually write that message also in red so that I show that this message is supposed to be a secret, and this D is also supposed to be a secret. But when this encryption is done, oh, sorry. The key that is used to do this encryption is not a secret. Okay. So one of the questions is already, how come they know all this information, but they cannot find M? Well, we have to actually go on and create specific encryption and decryption functions such that this property holds. But for now, I'm just saying what we wish for. So this is our wish. We want to have something like this so that we can have secure communications. This is just the definitions and the requirements. So just to reiterate here, we have two different keys. We have a key that is used for decryption, and this key is secret, only Bob knows it. So sometimes we just call this Bob's secret key because it's secret. And then we have another key, E, which can be used for encryption, and anyone can use it, and it's actually announced on the network, so everyone knows it. So it's public, so we call this Bob's public key. Okay? So now the question is, how do we actually create these keys? And the answer is going to need more time than we have today, so I will cover it in the next session. It's called the RSA crypto system. But the idea is actually very similar to what we saw here in Diffie-Hellman. So what we will do there is that we define these encryption and decryption functions so that if you want to compute M from this given data, it's very much similar to computing a discrete logarithm. Or in case of RSA, actually we use another hard problem, which is the problem of factoring when you're given a large number. So generally it's known that if you have a very large number, it's hard to factor it down. And what we will do is that we will show that if an adversary can compute M using this information, then they can likely factor a large number. Okay, but this is for the next session. For now, I just want to tell you some extra information here. Suppose that we have such a system. Suppose that we have a way of encryption and decryption that does this. We can, of course, use that for secure communication, because whenever I want to send an email to Bob, I just encrypt it using E and send the encrypted message to Bob, and I'm sure that only Bob can decrypt it. That's great. But actually, the same system can also be used for digital signatures. So what is a digital signature? Again, this is something that I will formalize in the next session. But suppose that Bob wants to sign something and wants to prove to us that he actually agrees with something. So suppose that, for example, you have a transaction that is going out of Bob's account and you need a proof that Bob actually allowed that particular transaction. So if that's the case, then we need to have some notion of a digital signature, something that proves to us that this message is actually coming from Bob. So if you think of a digital signature, it should be some proof that only Bob can create, because only Bob should be able to sign on his own behalf, right? And conceptually, this is very similar to decrypting here. So because in this scenario of public key cryptography that we have here, only Bob can do decryption, right? And then when we talk about digital signatures, only Bob should be able to sign. So in both cases, we have an action that only Bob can take. And actually, in the next session, we will see that when we solve the problem of public key cryptography using RSA, this also gives us a way of providing digital signatures. So Bob's way of providing a digital signature is pretty much the same as decrypting some message. And because only Bob can do it, then this proves to us that, okay, this was done by Bob. Okay. Yeah, so this is all for today. Feel free to ask any questions that you might have in the chat, and I will stay and answer the questions. And in the next session, we will cover RSA and basically say how we can create the encryption and decryption functions that have these desired properties. Okay, thanks. And yeah, this is the end of this session. I stop the recording.